Hello, and welcome to Lesson 21 of this Introduction to Differential Equations with Wolfram U. After studying methods to solve differential equations explicitly and with series techniques, we will now turn our attention to applying an integral transform known as the Laplace transform to differential equations. Before we can solve differential equations with the Laplace transform, we will need to discuss the transform itself. Let's take a look at an overview of this lesson. The techniques we have learned thus far for solving differential equations have proven to be extensively capable. With these techniques, we can solve a wide variety of differential equations either exactly or with series techniques. However, these methods can be somewhat awkward to utilize as different methods are required depending on the type of equation, and certain forms for the solution need to be assumed in some cases. A more straightforward method of solving differential equations is based on the Laplace transform. The Laplace transform possesses a multitude of useful properties that can be applied to solving differential equations. This transform is based on an improper integral where the upper bound is infinity. Such an integral would represent the area under the curve all the way out to infinity, as is shown in the plot here for part of the range. Before we can discuss applying Laplace transforms, we will need to discuss improper integrals and how to calculate them. Because the Laplace transform involves an improper integral, we will begin this lesson with a brief review of improper integration. An improper integral over an unbounded region is defined as the limit of the definite integral over a finite region. For example, the integral on the left is from little a to infinity. By definition, this integral is related to the definite integral from little a to some arbitrary but finite upper bound big A. The definite integral from little a to big A can be calculated, and the improper integral is said to exist if the limit of this result as big A goes to infinity exists. It is sometimes said in this case that the integral converges to that limit. The manipulate here demonstrates a definite integral. Here we are integrating sine of x over x from little a equals 0 to some upper bound big A. By moving the slider, we can adjust the upper bound. The shaded region is the area under the curve, which defines the definite integral, while the numerical value for the definite integral is shown in the plot. Creating such a plot is very easy in the Wolfram language. In the code, the first plot command makes the line, while the second plot command makes the shaded region, and the graphics text part calculates and displays the value of the integral, which is calculated numerically with n-integrate. All of these graphics are combined together with the show command, while the manipulate function is what creates the slider and lets us control the value of big A. If you would like to explicitly see the options that are being used, click on the plus sign and click on Uniconize. Let's take a look at calculating an improper integral. We will calculate the improper integral here, where f of t is equal to e to the minus t, and the limit of the integral goes from 0 to infinity. First, calculate the integral over a finite region, like from 0 to a, where a is some arbitrary positive number. We can calculate this definite integral from 0 to a in the Wolfram language using integrate. Now that we have an expression for the definite integral, take the limit of this solution as a goes to infinity. Therefore, we see that this improper integral is equal to 1. The Wolfram language can directly evaluate improper integrals by simply setting the upper bound equals to infinity, but of course it is important to understand how such integrals are formally calculated. As a second example, consider calculating the improper integral here, where f of t is equal to 1 over t, while the limit of integration this time is from 1 to infinity. Like before, begin by calculating the definite integral over the finite region from 1 to a, where a is greater than 1. With the definite integral obtained, take the limit as a goes to infinity. We can see here that the limit is infinity, so this is an example of an improper integral that does not exist. If you were to try to calculate this integral using integrate, you'll get a warning message indicating that the integral does not converge for this very reason. Thus, the output from integrate and the result of an explicit calculation of the improper integral agree. The Laplace transform is one of many types of integral transforms. Integral transforms in general take one function of some variable, like little f of t, and transform it into another function of a different variable, like big F of s. This transform is done by integrating the product of the function you are transforming, f of t, with some kernel function, k of s and t. Mathematically, this is represented by the integral here, where the bounds of the integral are arbitrary constants, alpha and beta, but normally take specific values for a particular transform. Different integral transforms will have different kernel functions and bounds on the integral, which is what distinguishes one integral transform from another. For the Laplace transform, the kernel function k of s and t is given by e to the minus s times t. The Laplace transform of a function f of t is represented by a big L with the function surrounded by curly brackets. For example, L curly bracket f of t is defined to be the function big F of s, which equals the integral from 0 to infinity of the kernel function e to the minus s of t times the function that's being transformed f of t. As we will see in future lessons, the Laplace transform can reduce initial value problems into quite simple forms. However, before we dive into applying Laplace transforms to the theory of differential equations, we will first look into the techniques of evaluating these transforms. Let's calculate the Laplace transform of the constant function f of t equals 1. Using our notation, this Laplace transform can be written as L bracket 1, which equals the function big F of s. Explicitly, the Laplace transform of 1 is equal to the integral from 0 to infinity of the kernel function e to the minus s times t times 1. Evaluating this improper integral in the Wolfram language with integrate gives the result of 1 over s. Therefore, the Laplace transform of f of t equals 1 is the function big F of s equals 1 over s. We can confirm this result explicitly with the Laplace transform function. Notice that the transform is only defined when s is greater than 0. If s is less than or equal to 0, then the integral will not converge. As another example, consider calculating the Laplace transform of e to the a times t for some constant a. This transform can be represented by L bracket e to the a times t, which equals the function big F of s. Explicitly, this Laplace transform is given by the integral from 0 to infinity of the kernel function e to the minus s times t times e to the a times t. This improper integral can be computed with ease in the Wolfram language. The result shows that the Laplace transform of e to the a times t is equal to 1 over s minus a. This can be confirmed using the Laplace transform function in the Wolfram language. Notice that this transform is only defined when s is greater than a. Integrate will give a warning message saying that the integral does not converge if s is less than or equal to a. We can see why this must be true. If s were to be less than or equal to a, then the exponent in the product of e to the a times t times e to the minus s times t would be positive or 0 when t is greater than 0, so the integrand would grow exponentially as t increases, which would make the integral not converge. For the Laplace transform of a function to exist, the function must satisfy a few properties. First, the function must be what is known as piecewise continuous. A function is said to be piecewise continuous on an interval if that interval can be partitioned into finitely many subintervals, where the function is continuous on each of those subintervals. For example, the function here is an example of a piecewise continuous function. Even though the function is discontinuous at -1 and 1, The function is piecewise continuous because we can break the region up into three separate regions. The first from minus infinity to minus 1, the second from minus 1 to 1, and the third from 1 to infinity. The function is continuous in each of these three subregions, so it is piecewise continuous over the full region. The second property a function must satisfy for the Laplace transform to exist is that the function must not diverge faster than exponential order. A function is said to possess this property if the absolute value of the function for some large value of the argument is less than or equal to an arbitrary exponential function k times e to the at. This property is required so that the e to the minus s times t term in the formula for the Laplace transform is sufficient to make the integrand go to 0 for large values of t. This ensures that the integral as t goes from 0 to infinity is finite. The two functions in the plot here are examples of functions of exponential order. As a final example, consider finding the Laplace transform of f of t equals 1 when t is between 0 and 1, while the function is 0 everywhere else. In order to calculate the Laplace transform, we must calculate the improper integral of e to the minus s times t times the function from 0 to infinity. However, since the function is 0 whenever t is greater than 1, we just need to integrate from t equals 0 to t equals 1. To show that both integration ranges will give the same result, define the function in piecewise form. With the function defined, integrate from 0 to infinity. This is exactly the same result we get when integrating just from 0 to 1 and using f of t equals 1 in that region. Therefore, we can say that the Laplace transform of this piecewise function is given by the result here. The Laplace transform function in the Wolfram language will give the exact same result. In this lesson, we have introduced the concept of an integral transform and discussed a specific integral transform known as the Laplace transform. The Laplace transform of a function f of t is the improper integral from 0 to infinity of f of t times e to the minus s times t, and is sometimes written as L curly bracket f of t or as big F of s. When calculating the Laplace transform, one begins with a function of the variable t. That function then gets transformed into a new function of a different variable s. We studied the necessary properties of the Laplace transform to exist in this lesson. In the next lesson, we will discuss how to use the Laplace transform to solve initial value problems.